In this video, we're going to focus on how to calculate the enthalpy change of a reaction. So consider the combustion reaction of ethanol, C2H5OH. In a combustion reaction, you have a hydrocarbon, which usually reacts with O2. The products of a combustion reaction is always going to be CO2 and water. Now go ahead and pause the video and balance the reaction. So notice that we have two carbon atoms on the left side. Whenever you're balancing a combustion reaction, balance the carbon atoms first. After that, move on to the hydrogen atoms and save the oxygen atoms for last. Since we have two carbon atoms on the left side, we need to put a 2 in front of CO2. Now notice that we have 6 hydrogen atoms on the left side. 6 divided by 2 is 3. Therefore, we need to put a 3 in front of H2O. Now notice that we have a total of 7 oxygen atoms on the right side. We have 4 from the 2 CO2 molecules and 3 from the 3 H2O molecules. We also have 1 in ethanol. Now 4 plus 3 is 7, and 7 minus 1 is 6. So we need 6 oxygen atoms from O2. 6 divided by 2 is 3, so we need to put a 3 in front of O2. So now the reaction is balanced. Now let's say if you're given the enthalpy change of formation for ethanol, let's say it's 278 kilojoules per mole, and for CO2 it's negative 393, and for H2O it's negative 286. So this is the enthalpy change of formation for each substance. How can you use this information to calculate the enthalpy change for the entire reaction? In order to do that, the enthalpy change of the entire reaction is the sum of the enthalpy change of formation for the products minus the sum of the enthalpy change of formation for the reactants. The products is everything on the right side. That includes the 2 CO2 molecules and the 3 H2O molecules. The reactants is everything on the left side. That includes ethanol, C2H5OH, and the 3 oxygen molecules. So now at this point, we need to plug in the heats of formation for each substance. So for CO2, it's negative 393 times 2 because we have a 2 in front, plus 3 times negative 286 for water, and ethanol is negative 278. Now, O2 is a pure element, and for any pure element in their natural state, the enthalpy of formation is 0. So this is going to be 3 times 0. So now we just have to do the math at this point. 2 times negative 393, that's about negative 786. And 3 times negative 286, that's a negative 858. And then negative 278, that's plus 278. And then the other one is just 0. So now let's add these three numbers. Negative 786 minus 858 plus 278. You should get negative 1366 kilojoules per mole. So that's the enthalpy of the reaction. And so as you can see, you can calculate it by taking the difference between the sum of the enthalpies of formation of the products minus the reactants. So what exactly is the enthalpy of formation of a reaction? the enthalpy of formation is the same as the enthalpy of a certain type of reaction. A reaction where a compound, 1 mole of a compound, is produced from its elements in our natural state. So let's write the reaction, the enthalpy of formation for the reaction of CO2. So we're going to produce 1 mole of CO2 on the right side. And it has to be 1. You can't change it to 2. Now the elements that make up CO2 are carbon and oxygen. And oxygen exists as O2 in its natural state. It's diatomic. So the enthalpy of this reaction is equal to the enthalpy of formation for CO2. Now let's prove it. We know that the enthalpy of reaction is always equal to the products minus the reactants. That is the sum of the products minus the sum of the reactants. So it's going to be CO2, which is the product, minus the reactants, carbon plus oxygen. By the way, this is a gas, this is a gas, and this is a solid. So the enthalpy of formation for CO2, in the last example we said it was negative 393. Now the enthalpy for a pure element is always 0. Thus, the enthalpy of reaction is equal to the enthalpy of formation for CO2. Why? Because we have only pure elements on the left side which have an enthalpy of formation of 0. And this is the only compound. So the enthalpy of that reaction will equal the enthalpy of formation. So as you can see, the enthalpy of formation is the same as the enthalpy of reaction for any substance that is produced from its elements in their natural state. Now, how would you write the reaction that's associated with the enthalpy of formation for water and ethanol? So we're going to put water on the right side. The elements that make up water are hydrogen and oxygen, both of which are diatomic. So we need a 1 in front of H2O. We can't have anything else. So the number of hydrogen atoms is balanced, but we have 1 oxygen atom on the right side but 2 on the left. So 1 divided by 2 is simply a half. So we need a half in front of O2. So now it's balanced. The enthalpy for this reaction is the heat of formation of water, which is approximately about negative 286. Now how would you write the reaction for ethanol, C2H5OH? So we're going to have 1 ethanol on the right side. The elements that make up ethanol are carbon, hydrogen, and oxygen. So we have 6 hydrogen atoms on the right side. 6 divided by 2 is 3. And only 1 oxygen atom, so we need a 1/2. And the enthalpy change of this reaction is equal to the enthalpy of formation for ethanol, which is negative 278. And let's go ahead and add the other one for CO2, which we wrote already. And so that's negative 393. Now, here's a question for you. How can we use Hess's law to estimate the enthalpy change for the combustion of ethanol? Basically this reaction, which we did already, but we didn't use Hess's law to get the answer. So how can we use Hess's law to calculate the answer that we had previously? So what we need to do is we need to adjust these 3 equations in such a way that they will add to the equation that we have on the bottom. So notice that we have 1 water molecule on the right side. So we're going to multiply this reaction by 3. And we have two CO2 molecules on the right. So we're going to multiply this reaction by 2 because we want two CO2s on the right. And ethanol is on the left side. So therefore, we need to reverse the third reaction. So for H2O, we wanted 3 H2O molecules on the right side. So we need 3 H2 molecules here, and this is going to be 3 over 2 O2 molecules. Now, if you multiply the reaction by 3, the enthalpy, you got to multiply the enthalpy by 3. So it was negative 286. So it's now negative 286 times 3, which is negative 858. That's the enthalpy change for this reaction. Now the next one was carbon plus O2, which turned into CO2. And because we had two CO2 molecules on the right side, we need to multiply this reaction by 2. The enthalpy change was negative 393, but we got to multiply that by 2. And so this is going to be a negative 786. Now for the reaction with ethanol, we had to reverse it. So we need ethanol to be on the left side. And on the right side, we have the elements that make up ethanol. That's carbon, hydrogen, and oxygen. The enthalpy of formation for ethanol was negative 278, but because we had to reverse it, it's now going to be positive 278. So what we're going to do is we're going to add these three reactions. So if we add them, notice that H2 cancels. We have 3H2 on the left and 3 on the right. So they completely cancel. In addition, the two carbon atoms cancel. They're on opposite sides. And that's about it. On the left side, we have ethanol, which is C2H5OH. So everything on the left is simply going to drop down. Now let's focus on the oxygen atoms. So on the left side, we have 2 plus 1.5 oxygen atoms. That's 3.5 on the left. But we have a half on the right. If we subtract half from both sides, this will cancel. And on the left side, instead of having 3.5, we'll have 3. Because 3.5 minus 0.5 is 3. So we're going to have 3 O2 on the left side. On the right side, these two would simply fall down. And it's going to be 2 CO2 plus 3 H2O on the right side. So now, if we add reactions 1, 2, and 3, and since we came up with this reaction, according to Hess's law, the enthalpy change of that reaction can be calculated by adding the enthalpy change of the individual reactions that we use to get this reaction. So we just got to add negative 858 plus negative 786 plus 278, and we get the same answer that we had in the last example, which is negative 1366. So you have two ways of calculating the enthalpy change of a reaction, using products minus reactants or even using Hess's law. Ammonia reacts with oxygen gas to produce nitrogen gas and water. So before we calculate the enthalpy change for this reaction, make sure you balance it. Pause the video and go ahead and balance it. So we can start out by putting a 2 in front of NH3 so we can balance the nitrogen atoms. And that would mean that we have 6 hydrogen atoms on the left side. 2 times 3 is 6, which means that we need to put a 3 in front of H2O. But now that we have 3 oxygen atoms on the right, to balance it, we need 3 over 2 in front of O2. So we can have 3 oxygen atoms on both sides. 3 over 2 times 2 is 3. To get rid of the fraction, multiply everything by 2. So we're going to double everything. So let's start by putting a 4. So if we have 4 nitrogens on the left, we need a 2 in front of N2 to make it 4. And notice that we have 12 hydrogens on the left side. 4 times 3 is 12. 12 divided by 2 is 6. And now we have 6 oxygen atoms on the right. 6 over 2 is 3. So now the reaction is balanced. Now let's say if you're given the enthalpy information for NH3, let's say it's negative 46, and for H2O, which is negative 286. Using this information, calculate the enthalpy change of the reaction. So to find it, it's simply going to be the sum of the products minus the sum of the reactants. So on the product side, we have 2N2 plus 6H2O, and on the reactant side, we have NH3 and O2. So the enthalpy information for any pure element that includes nitrogen and oxygen are 0. So this is going to be 0 plus 6 times the value for H2O, that's negative 286, minus 4 times the value for NH3, which is negative 46. And for O2 is 0. So 6 times negative 286, that's about negative 1716. And negative 4 times negative 46, that's positive 184. So if we add these two numbers, we can get the enthalpy change of the reaction. And so the final answer should be negative 1532. And typically the units is kilojoules per mole. Consider the following reactions. We're going to use Hess's law to calculate the enthalpy change of another reaction. Let's say the enthalpy change for this reaction is 1215. And the enthalpy change for the second reaction, we're going to say it's positive 283. So using these two reactions, calculate the enthalpy change for the combustion of methane. Methane is CH4, and it's going to react with oxygen to produce water and carbon dioxide. So what's the enthalpy change for this reaction? Feel free to pause the video and see if you can get the right answer. So you need to know what to focus on and what not to focus on. I wouldn't focus on CO because it's found in reaction 1 and 2. And I wouldn't focus on O2 because it's found in both reactions. Now, if you focus on CH4 and CO2, which is found in only one of those two reactions, it's going to make the problem a lot easier. So let's start by focusing on CH4. So if we look at the reaction that we want to calculate the enthalpy change for, notice that we have one CH4 on the left side. But here we have two CH4 on the right. So that means that we need to reverse reaction 1 and multiply it by 1/2. So I'm going to write R for reverse, and then times 1/2. So if we reverse it, CH4 is now on the left. And if we divide it by 2, we're going to have 1 CH4 plus 3/2 for O2. And then half of 4 is 2, so we're going to have 2 H2O molecules and 1 CO molecule. So how is that going to affect the enthalpy change of the reaction? Since we reverse it, the positive 1215 becomes negative 1215. And since we divide it by 2, we need to divide 1215 by 2. So this should be negative 607.5. So now let's focus on the second reaction. And let's focus on CO2. We have 1 CO2 molecule on the right side. Here it's on the left. So all we need to do is we need to reverse the second reaction. So it's 1/2 O2 on the left plus CO yields CO2. So the enthalpy change for that is going to be negative 283. So now let's add the two reactions. So let's see what cancels first. Notice that CO cancels. So we have 1 on the left, 1 on the right. And so this is going to fall down. So we have CH4. And notice that we have oxygen molecules only on the left. So we got to add. 1/2 plus 3/2 is 4/2. 4 divided by 2 is 2. So this is going to be 2O2 on the left side. And on the right side, all we have left over is the 2 water molecules and carbon dioxide. So we have the same reaction as this one. Therefore, to find the enthalpy change of that reaction according to Hess's law, we simply need to add these two numbers. So negative 607.5 plus negative 283, this is equal to negative 890.5. And so now you know how to use Hess's law to estimate the enthalpy change of a reaction. Another way in which you can measure the enthalpy change of a reaction is using calorimetry. So here's an example problem. 30 grams of sodium hydroxide was dissolved in 80 milliliters of water. The temperature increased from 27 to 70 degrees Celsius. Estimate the enthalpy change for the dissolution of NaOH. So how can we do this? How can we find the enthalpy change of the reaction? The first thing we need to do is find out how much heat energy was absorbed by the water. And we can do this using Q equals MCAT, MC delta T. Anytime you want to find out how much heat was absorbed or released by a substance, if you know the specific heat capacity of that substance, and if a temperature change occurs, use this equation. Now, the energy released by the reaction is equal to the energy absorbed by water. So Q of the reaction, in this case the dissolution of sodium hydroxide, is equal to the amount of heat energy absorbed by the water. Now, the amount of heat absorbed by the water is an endothermic process. Because the temperature of the water rose, it increased. Now, because the reaction released energy, it's exothermic for the reaction. So, the dissolution of sodium hydroxide is an exothermic process because it caused the surrounding water molecules to increase in temperature. Now, to find the enthalpy change of the reaction, it's going to be Q divided by N. Now, typically, enthalpy is represented in units of kilojoules per mole. And in this equation, Q is going to be in joules, so you have to convert it to kilojoules and simply divide it by moles. And you can estimate the enthalpy change for that reaction. So let's calculate the amount of energy absorbed by the water. So the mass of the water is 80. Keep in mind the density of water is 1 gram per milliliter. That means 1 milliliter of water has a mass of 1 gram. Therefore, 80 milliliters of water has a mass of 80 grams. The specific heat capacity for water is 4.184, and the units are joules per gram per Celsius. And 80 has the units grams. So as we can see, grams cancel. You need to understand what the specific heat capacity is, what it represents. It is the amount of energy needed to heat up 1 gram of a substance by 1 degree Celsius. So in the case of water, it takes 4.184 joules of water. It takes 4.184 joules of heat energy to heat up 1 gram of water by 1 degree Celsius. By the way, sometimes the heat capacity might be used in calories instead of joules. So the heat capacity of water is also 1 calorie per gram per Celsius. 1 calorie is 4.184 joules. It's another unit of energy, specifically heat energy. A capital calorie is equal to 1,000 lowercase calories. So these are some other units to know. The temperature change for this reaction is the final minus the initial temperature. So 70 minus 27, that's a temperature change of 40 degrees Celsius. So the unit Celsius will cancel. Therefore, Q is going to be in joules. So 80 times 4.184 times 43, that's about 14,393 joules. So that's how much heat energy was absorbed by the water. So the amount of energy that was released by the reaction is negative 14,393 joules. Keep in mind, it's endothermic for the water because the water absorbed energy, increasing its temperature, and therefore its kinetic energy. But it's negative for the reaction. It's positive for water since it's endo, but it's negative for the reaction because it's exo. The reaction released heat energy. Now we need to convert joules into kilojoules. Now keep in mind, 1 kilojoule is equal to 1,000 joules. So we need the unit joules to be on the bottom so that these units will cancel. And so the unit kilojoule is going to go on top. So to convert joules to kilojoules, you need to divide by 1,000. So it's negative 14.393 kilojoules. Now, in order to estimate the enthalpy change of the reaction, we need to calculate the moles of sodium hydroxide. Right now we have the grams. So we have 30 grams of NaOH. To convert it to moles, we need to find the molar mass. So we need to use the periodic table. The atomic mass of Na is approximately about 23. And for oxygen, it's 16. For hydrogen, it's 1. If you add these three numbers, you should get about 40. The unit for molar mass is grams per mole. So this is 40 grams per mole. What that means is that 1 mole of sodium hydroxide has a mass of 40 grams. So the unit grams of NaOH cancel. 30 divided by 40, we can cancel the 0. So this is basically 3 over 4. 3/4 is 0.75. So we have 0.75 moles of NaOH. So now we can calculate or estimate the enthalpy change of the reaction for the dissolution of sodium hydroxide as it dissolves into the sodium cation and the hydroxide anion. And now, the enthalpy change of the reaction, as we mentioned before, it's Q of the reaction divided by N. So we just got to divide the kilojoules by the number of moles. So it's negative 14.393 kilojoules divided by 0.75 moles. So you should get negative 19.2 kilojoules per mole as the final answer for this particular example. So that's how you can estimate the enthalpy change of a reaction using calorimetry. How would you solve this problem? The enthalpy of combustion for benzene is negative 3270 kilojoules per mole. How much heat energy will be released if 30 grams of benzene is burned in air? Let's focus on part A. So we need to write a reaction, a thermochemical equation, a balanced reaction that is associated with the enthalpy change of the reaction as well. So let's start with benzene, which we know is C6H6. Now, it's burned in air, so it's going to react with the oxygen molecules that's in the air. And in any combustion reaction, we're always going to get CO2 and water as the products for the reaction. So we need to balance the reaction. So we have 6 carbon atoms on the left side. We need to put a 6 in front of CO2. And since we have 6 hydrogen atoms on the left, 6 divided by 2 is 3. And if we count the oxygen atoms on the right, we have 12. 6 times 2 is 12, and 3 from water. So that's 15. 15 divided by 2 is 15 over 2. So at this point, the reaction is balanced, but we have a fraction with a denominator of 2. Therefore, we want to multiply everything by 2. So let's start by putting a 2 in front of benzene. So we now need 12 carbons instead of 6. Now we have 12 hydrogens on the left side, so we need a 6 in front of H2O. So at this point, we have 24 oxygen atoms from the CO2 and 6 from water. That's 30. 30 divided by 2 is 15. So now the reaction is balanced. By the way, the enthalpy change for benzene, the 3270, doesn't correspond to this reaction. Rather, it corresponds to this reaction. This is the amount of heat energy that's released when 1 mole of benzene is burned in air. It's the kilojoules per a single mole, not 2 moles. So therefore, the enthalpy change for the second reaction, this is negative 3270. So for this reaction, since it's multiplied by 2, it's going to be twice as much. 3270 times 2 is negative 6540. So now that we have the energy that's associated with this reaction, we can answer the question in part A. How much heat energy will be released if 30 grams of benzene is burned in air? So what we need to do is convert grams to kilojoules. So let's start by converting grams to moles. So we need to find the molar mass of benzene. So for C6H6, the atomic mass of carbon is about 12, but there's 6 of them, so we got to multiply 12 by 6. And for hydrogen, it's about 1, but there's 6 of them as well. 12 times 6 is 72, plus 6, that's 78. So there's 78 grams of benzene in a single mole of benzene. Now, in this thermochemical equation, it relates the number of kilojoules per mole. So, if 2 moles of benzene reacts, negative 6540 kilojoules of heat energy will be released. If 15 moles of O2 reacts, 6,540 kilojoules of heat energy will be released. If 12 moles of CO2 is produced, this is how much energy will be released in the reaction. So, depending on the substance, you can convert from moles to kilojoules using that connection. So, since we have benzene, we need to use the 2. So 2 moles of benzene will release this many kilojoules of heat energy. So let's write that in the next fraction. So we have 2 moles of C6H6 and that's going to release negative 6540 kilojoules of heat. So the unit grams cancel and also moles cancel. So now we can calculate the answer. 30 divided by 78 times 6540 divided by 2 is negative 1258 kilojoules. That's how much heat energy will be released if all of the 30 grams of benzene is burned in air. So now let's focus on part B. How many grams of CO2 will be produced if 8,800 kilojoules of heat energy was released from the reaction? Well, let's rewrite the reaction because I erased it. And the energy change was 6540, but negative. So this time, we need to convert from kilojoules to grams of CO2. So let's start with what we have. That's 8,800 kilojoules over 1. Now the connection between kilojoules and CO2 is that if 12 moles of CO2 is produced, 6540 kilojoules of heat energy will be released. So we can put the 6540 kilojoules on the bottom so that the unit kilojoules will cancel. And 12 moles of CO2 correspond to that amount of energy. So make sure you use the right coefficient that correlates to the substance that you're looking for. So now, all we need to do is convert moles of CO2 into grams. So we need to find the molar mass. The atomic mass of carbon is 12, and for oxygen is 16, but times 2. 2 times 16 is 32, plus 12, that's 44. Therefore, 1 mole of carbon dioxide has a mass of 44 grams. So now the unit moles of CO2 cancel. So 8,800 times 12 divided by 6540 times 44 is equal to 710 grams, 0.5 or 0.46. So I'm going to round that to 710. So 710 grams of CO2 will be produced if 8,800 of kilojoules of heat energy was released from the reaction. So now you know how to convert from grams to kilojoules and kilojoules to grams using a thermochemical equation. Now you need to be familiar with phase changes. Whenever a substance goes from the liquid state to the solid state, what is the process called? This process is known as freezing. Freezing, is it an endothermic process or an exothermic process? Do you have to add heat energy or remove heat energy? In order to convert, let's say, liquid water into ice, you need to remove heat energy because you need to bring down the temperature. So because you're removing heat energy, freezing is an exothermic process. Now the reverse, going from a solid to a liquid, is called melting. If you want to melt ice, you need to add heat to it. If you put ice on a stove and if you turn up the heat, it's going to melt. So melting is an endothermic process, which means that the enthalpy change is positive. Now, what is the process called when a liquid converts into a gas, and also when a gas converts to a liquid, and when a solid goes to a gas, and when a gas goes to a solid? Feel free to pause the video and identify the names of these physical processes, and also determine the sign of the enthalpy change. Is it positive or is it negative? Going from a liquid to a gas, this is called vaporization. And gas to liquid is known as condensation. Now, going from a solid to a gas, this is called sublimation. And what do you think gas to solid is called? What is that called? If a gas goes directly into a solid, this is called deposition. So vaporization, is it endothermic or exothermic? It turns out that to vaporize liquid water into steam, you got to add heat to it. So this is an endothermic process. It's positive. So condensation, which is the reverse, that's exothermic. You need to remove heat energy from steam if you wish to condense it back to liquid water. Sublimation, going directly from a solid to a gas. That doesn't happen with water, at least not under normal pressure conditions. But at a standard pressure of 1 atm at sea level, carbon dioxide sublimes directly from a solid to a gas. That's why it's called dry ice, because it doesn't liquefy under room temperature conditions, under normal pressure conditions. It goes directly from a solid to a gas, so it's dry ice. And as it goes from a solid to a gas, that's an endothermic process. It has to absorb heat energy to do that. Deposition is exothermic because it's the reverse. So let's see if we can summarize what we've just learned. As you go from a solid to a liquid, which is melting, and then a liquid to a gas, which is vaporization, going in this direction, the enthalpy change is positive. The process is endothermic. Now, if you go backwards, from a gas to a liquid to a solid, it's an exothermic process. Energy has to be released. So, solid to liquid, we said it's melting. Liquid to gas, vaporization. And going directly from a solid to a gas, this is sublimation. Now, gas to liquid, that's condensation. Liquid to solid is freezing. And gas directly to solid is deposition. All of those three processes are exothermic. Now, let's work on a few other problems related to thermochemistry. How can you calculate the amount of energy required to heat 50 grams of water from 20 to 60 degrees Celsius? To calculate the energy absorbed or released when given a temperature change, you can use an equation that we used earlier. Q is equal to mcat. The mass of water is 50. The heat capacity is 4.184. And a temperature change, final minus initial, the change is 40. So 50 times 40, that's 2,000 times 4.184. This is going to be 8,368 joules of heat energy. So now, what about a phase change? How can we calculate the energy absorbed or released when, let's say, water turns into ice, or if it vaporizes into steam. How can we do that? So let's say if we have 80 grams of ice, how much energy is required to melt 80 grams of ice into water? And let's say the temperature of the ice is at 0 degrees Celsius. And the temperature of the liquid water is also at 0 degrees Celsius. So before the temperature rises, all of the ice has to melt into liquid water. While ice melts into liquid water, the temperature will remain constant at 0 degrees Celsius. So we have a phase change problem as opposed to a temperature change problem. And so we need the heat of fusion. To calculate the amount of joules that's going to be released, or kilojoules, instead of using an equation, it's better to convert to get the answer. The heat of fusion for water is about 6 kilojoules per mole. So if you're going from solid to liquid or liquid to solid, you can use the heat of fusion. From solid to liquid, which is melting, that's an endothermic process. So it's going to be positive 6 kilojoules per mole. If it was freezing, which is exothermic, it would be negative 6 kilojoules per mole. So let's start with 80 grams of ice, which has the formula H2O. And let's convert that into moles. So the molar mass of water is 16 for the atomic mass for oxygen plus 2 for the 2 hydrogen atoms, which is 18. So there's 18 grams of water per 1 mole of H2O. So these units will disappear. And now we can convert moles into kilojoules. So for every mole of ice that melts to liquid water, 6 kilojoules of heat energy will be released. So it's going to be 80 times 6 divided by 18, which is about 26.7 kilojoules. So that's how much heat energy is required to melt 80 grams of ice. Now what about this one? How much energy is required to heat 50 grams of water from 20 degrees Celsius to steam at 170? And the heat capacity of liquid water is 4.184. The heat capacity of steam, or water in a gaseous state, we're going to say it's about 2 joules per gram per Celsius. The heat of vaporization for water is about 41 kilojoules per mole. So using this information, how can you calculate the amount of energy that's required to heat water from 20 degrees Celsius to steam at 170? So you need to realize that this is a multiple part problem. There's many steps. So let's say if we were to draw a number line. Water boils at 100. The current temperature is 20, and we need to get to 170. So we got to find out how much heat energy is required to heat liquid water from 20 to 100 degrees Celsius. That's Q1. Q2, that's the amount of energy required to vaporize liquid water into steam at 100. So that's a phase change. Q3 is the temperature change. That's how much energy is required to heat up steam from 100 to 170. So you got to break this problem into 3 parts. So let's calculate Q1. So because it's a temperature change, we're going to use the equation MCAT. The mass of water is 50. The heat capacity of liquid water is 4.184. And the temperature change of liquid water is from 20 to 100. Past 100, it's no longer liquid. So it has to increase by 80 degrees Celsius. That's 100 minus 20. So 50 times 80, that's 4,000 times 4.184. So it requires 16,736 joules to heat liquid water from 20 to 100 degrees Celsius. So now, let's focus on the second part, Q2, which is a phase change. So to calculate the energy required to vaporize water from 100 degrees Celsius to steam at 100, we need to do a conversion. So let's start with 50 grams of water, and let's convert it to moles. So we know that the molar mass of H2O is about 18, and the heat of vaporization for water is about 41 kilojoules per 1 mole. So grams will cancel and the unit moles cancel as well. So it's going to be 50 divided by 18 times 41. Now, you should get 113.9 kilojoules. But notice that the unit here is in joules. We're going to have to add Q1, Q2, and Q3. In order to add them, they must share the same unit. So we need to convert kilojoules into joules. So therefore, we can add an extra step. We can multiply this by 1,000 joules per kilojoule. And the unit kilojoules will cancel. So therefore, this is going to be equal to 113,889 joules. So now we need to find Q3, which is the temperature change. It's the amount of energy that's required to heat up steam from 100 to 170. So we're going to use the equation MCAT again. So the mass is 50. The heat capacity for steam is about half of that for liquid water. It's about 2 joules per gram per Celsius. The temperature change, final minus initial, that's 170 minus 100. So that's 70. 50 times 70 is 3,500 times 2. So that's about 7,000 joules. So notice that most of the energy that's required is to vaporize liquid water into steam. That's where you got to put most of the energy in. It takes a lot of energy to vaporize liquid water into steam. After that, it doesn't take much energy to heat up steam. So now let's find the total energy, which is the sum of Q1, Q2, and Q3. So 7,000 plus 16,736 plus 113,889. The total energy is about 137,625. So that's how many joules of heat energy is required to heat 50 grams of water from 20 degrees Celsius to 170. And if you want to convert this to kilojoules, divide it by 1,000. So this is 137.6 kilojoules. Now, what if you want to calculate the amount of heat energy that's required to heat up 80 grams of ice from negative 30 degrees Celsius to steam at 300 degrees Celsius? What do you need to do? Well, let's draw the heating curve for water. So first, we need to heat up ice, and then ice is going to melt to liquid water. Then we need to heat up liquid water, and then that's going to turn to steam, and then we need to heat up steam. So on the y-axis, we have temperature. On the x-axis, we have the amount of heat energy that we're adding to it. So this is the solid phase, which is ice. This is the liquid phase, water, and this is steam. On the horizontal line, we have the solid and the liquid phase coexisting. So the temperature that corresponds to it is 0 degrees Celsius. On the second horizontal line, we have the liquid and the gas phase coexisting. So let me write, instead of writing S for steam, I'm going to write G for gas. So there's 5 Q's that we need to calculate in this problem. We're starting at negative 30. So we need to calculate Q1. That's for ice, as we heat it from negative 30 to 0. So you need the specific heat capacity for ice, which is very similar to steam. It's about 2 joules per gram per Celsius. And then we need to calculate Q2. That's a phase change problem. That's the energy that's required to melt ice into liquid water. And then Q3 is a temperature change problem where we need to use Q equals MCAT. And we need to heat up liquid water from 0 to 100 degrees Celsius. Q4 is a phase change problem. We need to do a conversion. And we're going to vaporize liquid water into steam. And Q5, that's a temperature change. We need to use MCAT again. And we're going to heat up steam all the way to 300 degrees Celsius. So to solve this problem, you need to find Q1, Q2, Q3, Q4, Q5. Make sure they have the same unit, either joules or kilojoules, and then add them. So we're not going to actually do this example, but I just want to give you the guideline of how to do it or how to set it up. I just want to help you to see the process of solving it. By the way, keeping this in mind, as you add heat to ice, whenever the temperature increases, that's in these 3 segments for Q1, Q3, and Q5, the kinetic energy is increasing. So as you add heat, as the temperature goes up, the kinetic energy of the molecules increases. Now, during the horizontal part of the graph, that's Q2 and Q4, as you add heat, the solid in Q2 is melting into a liquid. And so, because the temperature is constant, you're not increasing the kinetic energy. What's happening is you're increasing the potential energy of the water molecules as you melt them from solid to liquid. The same is true for Q4. As you vaporize liquid water into steam, you're increasing the potential energy of the system. "70 grams of metal at 200 degrees Celsius was dropped in a bucket containing 40 grams of water at 20 degrees Celsius. The temperature increased to 32 degrees Celsius. Calculate the specific heat capacity of the metal." So now we're going to work on some heat transfer problems. This is one of them. And how can we solve this? So first, let's understand what's happening. So let's say if we have a bucket that has water and we add a metal to it. So initially, the temperature of the metal is 200 degrees Celsius and the temperature of the water is 20. So heat is going to flow from hot to cold. So heat is going to flow out of the metal into liquid water. So because heat is being released from the metal, it's exothermic for the metal. The temperature of the metal is going to go down. Now, since heat is being absorbed by the liquid water molecules, the temperature of the water is going to go up. Eventually, equilibrium will be established, and the temperature of the metal will decrease to a point where water, let me rephrase that. So the temperature of the metal is going to decrease and the temperature of the water is going to increase. At some point, at some temperature, these two will be the same. They're going to meet at some point. And that point is at 32 degrees Celsius. Once the temperature of the metal is the same as the temperature of the water, at that point equilibrium has been established. The temperature will no longer change. It's going to remain at 32. The amount of heat that leaves the metal is going to be equal to the amount of heat that goes back to the metal from the water. So at that point, the temperature will no longer change. That's the final temperature, which is the same for both. So now let's see if we can calculate the specific heat capacity of the metal. So the amount of heat energy that's released by the metal is equal to the amount of heat energy that's absorbed by the water. So whenever you have a heat transfer problem, where you have to set QA equal to QB, you need one side to be negative for this to work. Because on one side the temperature is increasing, and on the other side the temperature is decreasing. So to make sure the math works out, you have to have a negative sign on one side. It doesn't matter which side you put it on, as long as you have a negative sign, it's going to work. So let's go ahead and solve it. So Q equals MCAT for both sides. On the left side, we're dealing with a metal. The mass of the metal is 70. We're looking for C, the heat capacity of the metal, or the specific heat capacity. Delta T is the final temperature minus the initial temperature. The final temperature is 32 for both samples. The initial temperature for the metal is 200. The mass of the water is 40. The heat capacity is 4.184. And the temperature change, it's final minus the initial, which is 20. So we have negative 70 C times 32 minus 200. That's negative 168. 40 times 4.184, that's 167.36. And 32 minus 20 is 12. Positive 12. Notice that the two negative signs cancel, and it makes the left side positive, which is equal to the right side, which is also positive. That's why this negative sign is important. So 70 times 168, that's 1170, well, 11,760 times C, and 12 times 167.36 is about 2008.32. So to solve for C, we need to divide both sides by 11,760. So 2008.32 divided by 11,760, the answer is 0.17. That's the heat capacity for the metal. Notice that it's very low. The metal had a very large temperature change. Let's compare the two. So on the left side, we have the metal, and on the right side, water. So the heat capacity of the metal, we calculated to be about 0.17. For water, it's 4.184. Now, the temperature for the metal, it went from 200 to 32. That's a large temperature change. But for water, it increased from 20 to 32. So here, the temperature change is only 12. And on this side, the temperature change is 168. So notice that a substance with a very high heat capacity typically experience a very small temperature change for the same amount of energy. A substance with a very low heat capacity will experience a very high temperature change. Metals usually have very low heat capacities, which means that they can conduct heat very well. If you put a metal on a stove, the temperature of the metal is going to increase rapidly, almost instantaneously. Metals are good conductors of heat. Now, let's say if you pour water in a metal bucket and heat it up, the temperature of the water is not going to increase drastically quickly. It's going to take some time, because it takes a lot more energy for water to increase its temperature by 1 degree Celsius compared to a metal. So make sure you keep this concept in mind. Substances that have a very high specific heat capacity are usually associated with a small temperature change. It takes a lot of energy to raise the temperature. So water can store more heat energy than metal because it has a higher heat capacity. Substances with a very low heat capacity can't store a lot of heat energy. They can transfer heat pretty well. They're good conductors of heat, but they don't store heat energy very well. And so if you add heat to it, the temperature of such substances will increase greatly.